In this video, we solve problem 2.6.13 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to use the method for solving homogeneous polar equations to find the solution to this differential equation. Now we're given dx dt equals this. Now we know it's homogeneous polar. The differential equation is homogeneous polar because they tell us to use this method. But if they didn't tell us to use this method, we would know that this is a homogeneous polar equation because this function in the numerator and this function in the denominator are both homogeneous functions of the same degree. So while I'm not asked to show that this differential equation is homogeneous polar, since you guys are getting ready for a quiz in which you'll have to show that the differential equation is homogeneous polar, I'd like to practice with that here. Now, just as an aside, before we do that for this problem, I just want to remind you that a differential equation that is written like this, or can be written like this, excuse me, where f and g are homogeneous functions of the same degree is called a homogeneous polar differential equation. Now we say that a function is a homogeneous function of degree n if if that function f evaluated at tx and ty is given by t to the n times the original function. So if f satisfies this, then we say that f is a homogeneous function of degree n. So the degree of the homogeneous function is the power of t that we can factor out. Now, we have to use different variables for this problem because we don't have y as a function of x, we have x as a function of t. And this function in the numerator is a function of x and t, not a function of x and y, and the same is true for the denominator. So I don't want to replace t and x with t squared and tx because I don't want to use t in two different ways. So we have to modify this in order to verify that these are homogeneous functions of the same degree. So rather than using t here, since my original function was a function of t and x, I'm just going to pick a different variable. Instead of t, I'm just going to use the variable u. So we'll put ut here and ux there. If that can be written as u to the n times a function of t and x, then we're going to say that f is a homogeneous function of degree n. Notice that these are just exactly the same thing. I'm just using the variables in different ways. The only reason why I'm using this notation is so that I can verify that these functions of t and x are homogeneous functions of the same degree. So if I want to prove that this is a homogeneous differential equation, the way I do that is I show that this is a homogeneous function of a certain degree, and this is a homogeneous function of the same degree. Excuse me. Well, actually, I'll just say verify that f is a homogeneous function of a certain degree. So I've got f of tx and ty, or excuse me, f of t and x is 7x squared plus 9 times t times the square root of 5t squared plus x squared. Now, in order to verify that that's homogeneous, I'm going to replace each variable with the variable times u. If we can factor out a power of u when we're done, then, and we are left with the original function times that power of u, then it's a homogeneous function of whatever that power is of that degree. So we're replacing x with t or ux, and we're replacing t with ut. And this is what we get. We have ux here, ut here. If we square both of these factors, that's what we should do. You have a product squared, square each factor. And then notice when you look at this term and this term under the radical, they both have a u squared in common. So you want to factor that out. Oops, and this is supposed to be squared. It's squared there because that's x, that x is squared there. U squared times 5t squared gives me the first term, and u squared times x squared gives me the second term. The square root of a product is the square root of the first factor times the square root of the second factor. The square root of u squared is actually the absolute value of u, but if u is positive, we just get u. And this factor can't be simplified. That's for u being non-negative. And now we have this, 7u squared plus 9u times u is u squared times t times the square root of 5t squared plus x squared. And if I factor out a u squared from this expression and this expression, I have u squared times 7. Oops, I don't know how I dropped the x squared there. Times 7x squared plus 9 times t times the square root of 5t squared plus x squared. And that is my original function f of x and t. So I've got u squared times, or f of t and x. So since f of ut and ux is u squared times f of t and x, this function f is a homogeneous function of degree 2. So now we've verified that that is a homogeneous function of degree 2. Now we want to show that this g of t and x is also a homogeneous function of degree 2. That one's more obvious. You can just add the exponents and see that that's a degree 2 polynomial. Now remember that the differential equation is a homogeneous polar differential equation if we have a quotient of homogeneous functions of the same degree. And so it's not enough to just have it's not enough to just have homogeneous functions. They have to be of the same degree. In order to verify that this is a homogeneous function of degree 2, so that we have a homogeneous polar differential equation, I will replace each variable with that variable times u. So t gets replaced with ut and x gets replaced with ux. And you can factor out a u squared. That's u squared times 7 times t times x, which is u squared times the original function. So g is also a homogeneous function of degree 2. Since that's true, we've got 2 homogeneous functions of degree 2. That means this differential equation is a homogeneous polar differential equation. Okay, now we weren't asked to show that, but you may be asked to do that on a quiz in my class. So it was a good opportunity to review. Okay, now that you know that you have a homogeneous polar differential equation, we want to take that differential equation and we want to write it as a function of x over t. So what I would recommend, since we have a monomial in the denominator, is that you take each of these terms and divide it by 7 times t times x. So you have 7x squared divided by 7 times t times x plus 9t times the square root divided by 7 times t times x. You want to simplify wherever you can. The 7s will reduce, one of the x's will reduce, the t's will reduce, and now you've got an x over t there, and that's what you want. That's going to be our new variable. We're going to call that v. Now this you have to write in terms of x over t as well. Let's do that on the next page. I have 7 times x in the denominator, and I'm still trying to write this as a function of x over t. In order to do that, I'd like to write all of this under one radical. I can make that happen if I square the x and take the square root. That's equal to x as long as x is non-negative. So we'll write that over here. We're going to replace x with the square root of x squared, which is true if x is greater than or equal to 0. If x happened to be negative, you just multiply it by -1. Now I've got a square root of a quantity over a square root of a quantity, and of course that 9 over 7 we can just factor out. Now, if you have a square root of a quantity over a square root of a quantity, you can write that as a single square root. You have an x squared down there. And now you have 2 terms divided by a monomial under that radical. So you can take each of those terms and divide by the monomial. You're just sort of separating that numerator into 2 pieces, because if you have a over c plus b over c, you'd keep the common denominator and add the numerators. That works backwards as well. So we're going from something that looks like this to something that looks like that. And then of course you can simplify. And then if I've got t squared over x squared, that can be rewritten as t over x quantity squared using that property. Now remember, we wanted this to be a function of x over t, not t over x. But t over x is just x over t to the -1 power, because if I take this fraction and I raise it to the -1, I just end up flipping it. So this is the same as this. I can flip that fraction as long as I say that t over x is actually x over t to the -1. If I take in a quantity to the -1 and I square it, I just multiply those exponents and I have that quantity to the -2. So we have written dx dt as a function of x over t. And now we are ready to substitute. So we're going to let v, that's just some variable that we made up, equal x over t. Then you want to solve for x, because x is a function of t here. I'm multiplying both sides by t. And then we want to compute dx dt using the product rule. And we're doing all of this because we'd like to write this as a function or a differential equation involving v and t rather than x and t. So if v equals x over t, that means x is equal to v times t, where v is a function of t. And that means dx dt is this according to the product rule. Derivative of the first times the second plus the derivative of the second with respect to t times the first. Okay, and then you're going to make a substitution. You're going to write all of this in terms of v and t. Now, some students get a little confused here because we're using a different substitution than we're accustomed to. We're used to writing the differential equation in terms of v and x. Now we're using x as the dependent variable. It can kind of confuse people. Basically, what you're trying to do is get rid of the dependent variable. So last time we were trying to get rid of y. This time we're trying to get rid of x. So we're going to replace this dx dt with this, because that's what dx dt is in terms of v and t. I call this dE star. This is my transformed differential equation. That equals what we have on the other side. Now, x over t is v. So that's v, and that's a v. So we have v plus 9 over 7 times the square root of 5 plus v to the negative 2. And you want to subtract v from both sides. So those will reduce. And then you have this. Now, in order to get this dt in the numerator multiplying a 1 over t, so I've got a function of t times a dt, I'm going to take the reciprocal of both sides. And I'm going to change the order in that multiplication. So I'll have 1 over t times dt dv equals 1 over 9 over 7 times the square root of 5 plus v to the negative 2. And I want all the v's on this side, so I'll multiply both sides by dv. And this is like they're canceling out. They're not exactly canceling out, but it's like they're canceling out. And then we want to anti-differentiate each side with respect to the variable that's there. The antiderivative of 1 over t with respect to t is just natural log of the absolute value of t plus a constant. We're going to let the constant on this side absorb the constant from that side. Now this one we don't have a rule for, but if we do a little bit of algebra, it turns out that we will have a rule for it. So what I would suggest is simplifying from here. So let's see. We've got 1 over this fraction. So we can flip that fraction. That 9 over 7 would become a 7 over 9. And then this over here can be written as 5 over 1 plus 1 over v squared. Now, if I want to get a common denominator so that I can simplify this further, I'll multiply this by v squared over v squared. And what we end up with is 5v squared plus 1, all divided by v squared. And then we have 1 over a fraction again, so we can flip that. Now again, we've got the square root of a over b. If we want, we could write that as the square root of a over the square root of b. And that will help us. The square root of v squared is just v as long as v is non-negative. And then we have that. So we have natural log of the absolute value of t is equal to this. Now, if I want to evaluate that integral, I just have to do a u substitution. So let's see, what did we do? We wrote the differential equation in terms of v and t, and then we separated the variables. And then Our goal is to anti-differentiate, but we weren't able to anti-differentiate this side until we did a lot of algebra to write it in this form. Now that it's in this form, we can anti-differentiate. Excuse me. If I let u be the expression under the radical, then du is 10 times v dv. We don't have a 10 v dv, but we do have a v dv, so we can get rid of this 10 to solve for that v dv. Turns out that v dv is 1/10 of du. And then we can write the integral entirely in terms of u. So we have natural log of the absolute value of t equals 7/9 times this. V dv is 1/10 of du. I'll factor out the 1/10 and I'll put the du on the far right. That's this piece. And this is a square root of u in the denominator. And so we have 7/90. And then this we can rewrite as a u to the 1/2 power, but it's in the denominator. So we'll bring that up to the numerator, call that u to the -1/2 power. Now it's not necessary to write this in this form, but it is necessary to write it in this form so that we can take the antiderivative. Like these are equal to each other. The benefit of writing it like this is so that we can use the power rule to take the antiderivative. So we will bring our 7/90 down, add 1 to the exponent, and then divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2/1. Don't forget to add c. 2 goes into 90 45 times. That's going to be a square root of u. But remember what u is. U is 5v squared plus 1. Okay, so that was a lot of algebra so that we were able to do the u substitution. And once we were able to do the u substitution, we have this solution to the separable differential equation in v and t. Now we want to go back to x and t. So now we have to back substitute. Remember, v is just something that we made up so that we could compute the antiderivative, so that we could write it in a form so that we could solve the differential equation. Now we need to go back to x and t. So we're going to replace v with x over t. And you could leave it that way. You could try to simplify if you want to. It's not necessary though. You could just stop here, or I would stop here for a quiz. But that's not an answer that they're going to want in MyLab Math. They say, ignoring any lost solutions, if any, an implicit solution of the form f of t and x equals c is some function of t and x equals c, where c is an arbitrary constant. So they basically want you to get the constant by itself. So we would subtract this function from both sides. That would be the version of the answer that MyLab Math is requesting from us. It should be an equal sign. And obviously that's a very implicit solution. We could probably solve for x though. We could subtract this from both sides. We could multiply by the reciprocal of that. We could square both sides, subtract 1, divide by 5, take a square root, and then multiply by t squared. Or, well, take a square root and then multiply by t. But they wanted us to stop here, so we will.